Thank you, everyone, for joining for the session today. It's late afternoon, I realize it, and my goal is to have at least half of you awake by the end of the session. All right, today's topic is really exciting, at least for me. I'm going to talk about how Netflix leverages multiple AWS regions to increase availability and resiliency. It's a case study of two projects that we've done this year called Isthmus and Active-Active. But first, we can't really talk about availability and resiliency before we cover this everybody's favorite subject, failure, in all its glory. Broken systems, developers scrambling and panicking, customers flooding the customer service lines, everybody on Twitter telling you exactly what they think about your service being down, all that jazz. Most importantly, after we talk about failure, we're going to talk about how you can, in many cases, prevent or mitigate the impact of that failure. And we're going to go through some pretty interesting case studies. So let's talk about the failure itself. Let's set up some basic assumptions. One of the most fundamental assumptions is that the rate of failure is really a function of scale and speed. And so as you start out, things are slowly changing. You're at pretty small scale. Chances are most of the time things just work. That's fairly easy and fairly boring scenario. So let's make it more interesting. Let's say you still keep your pace of change fairly slow, but your scale grows. In that case, chances are the most of the type of failures you're going to encounter is a hardware failure, purely because of low in scale and statistics and possibilities. If, on the other hand, your scale stays small, but you want to run as fast as you can, your pace of change is really, really fast, chances are most of the time you're going to experience software failure. Basically, you're going to shoot yourself in the foot most of the time, pushing bad code, bad configuration, you know it. Now, the really fun part starts if you're running at scale and fast. Then everything is just broken. And so we're just going to focus on that one quadrant because the rest are just not challenging enough. Now let's apply some typical labels on these environments. Enterprise IT is typically what, slow changing, fairly small scale. Telcos run at scale, but their pace of change is fairly slow. Startups, on the other hand, are really fast because you're always running against time. Then again, your scale might not be as big. And here we have a few companies like Netflix that run at web scale. We also try to run really, really fast like a startup, except our order of magnitude of requests and scale and everything is slightly more interesting. Let's also define problems, incidents, because they do vary in severity. The ones on the top of the pyramid are the ones you really don't want to experience, ever. These are the ones that impact your public relations. When you see articles, service A is down, service B is down, people take it to Twitter, people take it to your customer service. And these are the type of incidents we really want to focus in this talk. And the claim is that you can mitigate some of them, not all, but some of them, by solutions like Active-Active and interesting practices called game day exercises. And then you have slightly less severe incidents that perhaps don't affect all the customers, and yet you still generate some huge number of customer calls into your system because some things are not working. And then for that, you do need better tooling and early problem detection and automation to mitigate some of those. Then there are far less severe issues that purely deal with the data that your application generates. Even though you might not be affecting customer experience, the data that you're getting upon which you typically need to make further business decision. Do you go with a feature A or feature B? Do you expand this UI or that UI? Data comes garbled. Garbage in, garbage out. And so that needs to be mitigated by better data tagging, cleanup, and just being mindful of what you see so you can actually make the right decisions. And last is really the no impact issues, things like the type of failures that can be easily solved by either retrying, automatic failover, and those are not quite as challenging, so we're not going to even talk about them. Let's talk about the scope of failure. Does an instance fail? Yeah, it does, and you should plan for it. Most of the time, again, it's going to be the code that you push, the code, the configuration. You're going to shoot yourself in the foot, especially if you move fast. But sometimes it could be latent issues. You could deploy something that works well for a period of time, and then it goes into a GC hell or some other fun issue. Or it could be more rare, but it could be a hardware failure. And so you should plan for it. For us, we deploy everything in a ASGs of more than one. And we also test things with KS Monkey. More on the Monkey later. But Monkey really does what the name says. It kills an instance at random, in test and production. But chances are you do want to do it yourself rather than find out that your application is not resilient when it happens at 3 o'clock in the morning. What about a zone? Does a zone fail? That's a much more rare occurrence. I mean, zone, after all, is a single or a collection of data centers. And so conditions at which zone fails are far more complex and far in between. But it did happen before. There were weather phenomena that triggered the power failures in specific zones and such. Sometimes there were routing issues. Or sometimes, once again, you shoot yourself in the foot with a bigger gun where all of your instances in a particular zone just go dead. So again, for Netflix, our availability goals are high, and so we stripe all of our deployments across multiple zones. And then we also exercise a bigger simian, Chaos Gorilla. And it does what you think it does. It basically brings the zone down in test and in production. Again, we want to do it during the daytime hours where engineers are there, where we can observe the behavior, where we can fix it if something goes wrong, but we'd rather do it under controlled conditions rather than have it to happen in the middle of the night. This one is interesting. Does a region fail? That's really, really unlikely. The conditions at which a collection of data centers all suddenly become unavailable are so catastrophic that I suspect people will have larger issues to deal with than worry about their Netflix streaming. That being said, as I mentioned, our availability goals are really high. Our internal availability goals is 4 nines of availability. If you do the numbers, that leaves you about 53 minutes a year not to be available. And so given the scale and the complexity of applications we're running, it's not an easy task. And so just like with instances and zones, we do deploy our services across multiple regions. And we test them, and I'm going to go more into that. We test them to withstand any single region outage and also a network partitioning event between the regions. We call that simian chaos Kong. We let them out of the cage a little bit more carefully because the results could be a bit more disastrous, but it does it damage, and then we see how our systems withstand it. So to summarize, if you give it enough scale, speed, and time, everything's going to fail eventually. Not to make things sound too gloomy. That being said, once you know about it, you can actually do something about it. What you can do is embrace two fundamental principles, and base and architect your system based on that. And if you do it right, you'll be able to withstand more or less severe outages without significant loss of quality to your users. Those principles are isolation and redundancy. To rephrase that, your challenge in writing cloud-native applications is to construct something that's resilient, agile, yet built on pieces that are effectively ephemeral. So how do you do that? So first, let's define what we mean in this context by isolation and redundancy. Isolation. In this particular context, isolation means that changes in one region should not affect the other, at least right away. Regional outage should not affect other regions. And also, a network partitioning event between two regions should not affect functionality in either one. So they should be resilient to such network partitioning events. That's isolation. Redundancy is much easier. Make more than one of anything. If you deploy your application, stripe it across zones, stripe it across regions. We're going to talk a little bit more in detail of mechanics of such deployments. So a little bit of history of kind of genesis to these projects of Isthmus and Active-Active. Last Christmas Eve in 2012, Netflix had a multi-hour outage. And it was particularly painful because it was Christmas Eve. So instead of enjoying quality entertainment, people were forced to spend time with their family. Now, AWS quickly triaged and fixed the root cause, which was caused by elastic load balancing issue. This is a quote from postmortem, that some state data in ELBs were deleted by a maintenance process that was unfortunately run against the production ELB. And the good news that only 7% of running ELBs were affected. Unfortunately, the control plane overload preventing any other ELBs from scaling. And so we had some ELBs that were affected, and we could not do anything about it. Again, we take our availability very seriously, and so very shortly after, we had a little powwow and think, what can we do about it? So out of that, Project Isthmus was born. Now, Isthmus name is for geographical features. geographical feature of a very thin strip of land surrounded by water that connects bigger pieces of land, like Isthmus of Panama. In this particular case, Isthmus is a tunnel that connected US East and US West. Our normal operations were in US East region, where in US West we deployed a completely separate bank of ELBs, and then we deployed some other infrastructure to support it, namely Zool. I'm going to focus on Zool in a little bit more, in a bit more detail shortly. And the way it would work is that we would geo-route some of the customers to US East ELBs and geo-DNS route some other customers to US West ELBs. That would be the normal state. In the event that ELB issue would happen again, we would go into a failover mode where we would force change DNS to route all of the customers into a surviving region, and then all the traffic would still be routed to the backend that could service user requests. So let's dissect Isthmus a little bit more. As I mentioned, one of the key components in this whole architecture is Zool. Zool is a really reliable, scalable, flexible API routing layer that allows us to do quite complex things. In this particular case, it maintains a bank of persistent connections between the regions. So then we don't have to do the three-way handshake every request. And the request that we forward from US West 2 ELBs goes to US East 1 backend. The responses come back, everybody happy. There is no latency penalty or no significant latency penalty in this case. There is some supporting infrastructure that we had to make. So first we had to make some changes to our service discovery infrastructure called Eureka. In this diagram it's called discovery, where by default it's regionally isolated. In this particular case, we had to enable it to peek into another region to see how to route the request properly. We also had to extend a couple of our Cassandra clusters to replicate necessary state, and some other functionality that's really more internally driven rather than externally functional. So let's talk about Zool in a little bit more detail. As I mentioned, Zool is our API routing layer, and it's really the front layer of defense where all the requests come in. Right after ELBs, all the requests come and are handled by Zool. And at the core of Zool is really powerful yet flexible routing engine, where you could dynamically load and change dynamically executed Groovy scripts. And the degree of flexibility is pretty high. You're able to execute the script filters before the request is handled, at the request handling time, and post-request handling time. And this way you can really define fine-grained, even using regex, routing rules for a lot of the requests. In this particular case, we could say, okay, everybody west of Mississippi needs to go here, everybody east of Mississippi needs to go here. Zool handles misroutes, Zool handles load shedding in case of a thundering herd, a whole bunch of other things. We also realized that one other potential single point of failure was a DNS layer. That's even before you hit any endpoints. And so we created an open source denominator library that abstracts the DNS layer. This way, no matter who your DNS provider is, if for any reason they become unavailable, you can use the denominator library, make the same calls, just write into a different provider, and you can still do it. Well, this is great, and we tested it out. We gradually moved the traffic from east to west, back to east, all kinds of combinations, again, just to make sure it works under normal and extraordinary conditions. But it only works for elastic load balancing type of failures. How do we achieve greater availability? We decided we did not want to pursue one-offs for each of the possible combination of services failing. And they can. Again, possibility is very low, but they could. Thus, we decided to embark on a project we call Active-Active, which is a full regional resiliency. And in this particular case, the architecture changes slightly. We deploy our full stack of services in both regions, US East and US West. And under normal conditions, the user request would still be geo-DNS routed. Everybody east of Mississippi goes to east, west of Mississippi goes to west. Now, in case of zone outage, we actually don't need to do anything. We exercise Chaos Gorilla. We don't need to do anything. Everything else works. The surviving zones scale up. We handle traffic. Everything is pretty. But if the issue persists region-wide, or again, you have an issue at the edge somewhere, we go into a failover mode. where we override DNS, route all the customers to the surviving region. We have to scale it up, of course, and we're still in business. Again, let's go in a little bit more detail in the active-active architecture. We were a little bit lucky at Netflix because several years ago, we embraced the cloud all in. As a part of that migration to the cloud, we rewrote most of our applications, and one of the patterns we adopted is that most of our applications are stateless. To have a redundant deployment in such a case is really easy. All you have to do is just deploy your application in both places at once. However, not every single application can be completely stateless, and so you're going to have to replicate state somehow. That's going to be the trickiest part of this deployment. Now, the stateless part, we basically replicate in both regions as edge applications, middle tier applications, backend applications. Everything works well. When it comes to replicate state, we went with multi-region Cassandra clusters. Now, we already employed multi-region Cassandra clusters to synchronize data between our US East and EU West deployments. However, the conditions for this replication are slightly different because customer cannot be in US and Europe at the same time. There is some minimum flight time involved. And so we have decent SLA in replicating the data. Now, because of various network routes, and customer could be on a mobile phone and a tablet at the same time, or mobile phone TV at the same time, their request could be routed potentially to both regions in a fairly short period of time together. And so our SLA of replicating the data was much smaller. Now, Cassandra, if you know Cassandra's technology, it does embrace eventual consistency. But what we set out to prove is that eventual consistency doesn't mean hopeful consistency. In particular, that the eventual consistency replication is good enough for our use cases. Doesn't mean it's good enough for all use cases, but for ours. And so what we set out to prove is that one of our most highly loaded clusters could replicate data fast enough, so even if user two subsequent requests hit two different regions, he's still going to get a consistent user experience. So we set out to do that. One of our heaviest utilized clusters is the cluster that receives bookmarks. This is when you watch devices send bookmarks and heartbeats to the system to indicate where you are. This way, if you paused or somehow your session is abandoned, you want to resume, you resume from the same place. That's a very heavy traffic downstream. And so we replicated one of such clusters in test. It was basically a 96-node SSD cluster, 48 nodes on each side. And then we set it up with a copy of that data, approximately 18 terabytes of data. That's on the order of magnitude of what we store there. And then we applied the test load to replicate exactly the conditions under which the cluster operates in production. The test load simulated what the traffic that cluster typically experienced on a peak night when everybody is watching. So to validate that the replication works, we sent a validation load in the US East where we wrote 1 million writes in a CL1 level. CL1 level is basically you write at least one of the instances in the cluster X, you're done. You don't look for quorum, you don't look for read after write confirmation, you just write. After 500 milliseconds, we did a read, again with the same CL1, just give me any data that you have of any instance. One instance X, that's it, you don't look for quorum, nothing. From the other region. And after a million of such writes and million of such reads, we haven't lost a single piece of data. Now, 500 milliseconds, for most of our use cases and applications, it works well, so we didn't have to go any further. Unfortunately, Cassandra is not the only layer in which we had to replicate state. For many of our applications, the read latency SLAs are so tough, so they have to be so low, like low single-digit milliseconds, that we have to front them with a memcache layer to get those read SLA latencies. And so we already had our own memcache client called EVCache, and it does a few interesting and useful things for us, but we had to enhance it. We had to enhance the EVCache client in order to replicate the memcache state across region. Now, we really didn't want to re-implement or reinvent multi-master data replication in a memcache layer. It's a nasty problem, not the one we particularly wanted to solve. But the common use case that we needed to solve was to invalidate caches in a remote region. And that does involve a little bit of creating drainers and writers and propagating metadata. So effectively, if you have a write in one region, then you have to deposit something in a metadata store, notify drainer in one region, propagate the information to another one, update some metadata, invalidate cache, and then ACK to the metadata in the other region. Simple. One other thing we had to do is change the way we do configuration. Now, in Netflix, we very heavily rely on super powerful dynamic configuration tool we use called Arceus. We do perhaps tens or hundreds of code pushes a day. Well, we do hundreds to thousands of configuration changes a day in production. And what we found that by default, because it's so easy to do, by default, all the configuration changes had global scope, sometimes unintentional. When that happens unintentionally, there could be severe consequences to it. And so what we decided, rather than leaving the default global, is changing the default to be region local in scope. Now, push comes to shove, it's an emergency case, you do need to push a change that affects all the services globally, our developers can still do it. But by default, we want them to be aware that their change is region local, and that really is aligned with that principle of isolation. Another thing that we provided to our developers is complete transparency. On this screenshot, you can see that as developer types in the change and decides on a scope for the change, whether it's instance, cluster, ASG, zone, or region, he can immediately see how many instances will be affected by that change. And this way, there's not going to be any surprises where somebody wanted to debug something on one instance and affected tens of thousands instead. So this goes as far as actually building the system. Running it is a little bit more interesting. You build the beast, let's run it, right? Once again, at Netflix, when we need some operational help, monkeys to the rescue. We enhanced our Conformity Monkey to detect cross-regional deployment failures. This is for the case where you want to deploy your application in both regions, and yet part of the automation fails silently. You don't want to find out 2 weeks later that you're running 3 weeks old version in one of the regions. And so Conformity Monkey is looking for the version differences between the regional deployments. And up to a certain period of time, it does have some grace period, because sometimes we actually want to canary some changes in one region before propagating them to another. And after enough period of time elapsed, it will alert you that, look, by the way, you are running 2 different pieces of code. Is that on purpose? It will also alert you in differences in configuration. Once again, configuration differences sometimes could be on purpose. For example, we want to read different catalog of movies in Europe than in US. Sometimes they are intentional. Sometimes it could be something that's left from an experiment that they forgot to clean up. Conformity Monkey will alert you. We had to enhance greatly our monitoring. Now, we generate a lot of metrics and logs, and that all goes into our central monitoring system. What we had to do is enhance it that besides just providing visibility and transparency into what's happening within a region, we also needed to aggregate into a global view and also understand the patterns so we can plug in our automated anomaly detection tool and say, you know what, US East is going okay, but US West might be having some kind of a glitch. You better check this out. Exercising failover and fallback, we couldn't just build it, leave it running in stable state, and say we're done. We actually had to exercise the failure scenarios to validate that it works as expected. The exercising failover is rather easy, I'd say. Just enact the DNS changes, route the customers, you're done. Well, not quite as easy as that. You have to deal with interesting challenges such as cold caches. You have to deal with interesting challenges such as thundering herd of customers suddenly comes to a system that's underscaled. So how fast can you scale up? And so for that, we had to experiment, iterate, automate, iterate again, find new issues until we got it right. Fallback is a little bit trickier, the fallback out of the evacuation scenario, because before you can actually enact the fallback, you need to ensure that your region that prior was sick and now is healthy, now has a consistent state of data that perhaps it didn't have before. And so we developed tooling to indicate when we can actually have the green light for the fallback, even if all the services are running, the data is actually ready and we're ready to receive the customer traffic again. And again, validating the whole thing works, there is only one way for us to do it. because let simians loose in it. There's actually 3 different simians that we'll let loose in this case. Chaos Gorilla, again, to revalidate that after changing our architecture so much, we can still withstand any one zone outage. Chaos Kong, the more dangerous beast, but we had to validate this. And there is another monkey that internally we call the split brain monkey. And yeah, it does what you think it does. It separates all network traffic between the 2 regions. And what we want to validate that regions can function in isolation without lowering quality of service to our end users. And they actually all worked, especially with the split brain case. After we re-established network connectivity, Cassandra cluster synced up the data, EV cache synced up the data, everything is back in business. In Netflix, all the developers operate the applications that they write. We don't have a separate operations team. But what are the best practices when you're actually running your application at scale in multiple regions? For us, if you saw the graph on one of the earlier slides, traffic is highly cyclical. People come from work, people come from school, they start watching movies. And so what we don't want to do is make changes in production as much as possible during those times. And then when people finally go to sleep or they go to work, they go to school, that's our open window to start making changes again. This way, not if but when we make errors in production, less users will be affected. We also focus on minimizing the time to detect a failure and minimizing the time to correct a failure. And in this particular case, the automation, the automated canary analysis, automated testing and rollback becomes absolutely invaluable tool. And that's really orthogonal to whether or not you're running in multiple regions. It's just plain common sense and good practices. So to summarize, this is what we call a hyperscale architecture, where you have redundancy in every layer, starting from DNS and going down the stack, where you isolated services to withstand outage and sync every instance, every zone, or even at the regional level, even at such a critical place as DNS. Well, that all sounds great in theory, but does it work? So this is a snapshot of our monitoring graphs from a couple of weeks ago, where you'll see in US East there was a blip. The traffic is not quite as smooth as it should have been. Once again, we shot ourselves in the foot. We deployed a configuration change that wasn't as thoroughly vetted and tested as we would like, and it affected a couple of our applications. And unfortunately, some of the users were affected. But to validate the whole principle of isolation, you see that services in US West kept chugging along without any disturbances, disruptions, or loss of quality to the users. If you're doubting that we're exercising chaos monkeys or gorillas or kongs or other simians, we actually exercised chaos gorilla in production last week. Anybody noticed? Good. All right. So this is all fun and great, and Netflix did it. What about you? Can you do it? So this is the best bit. All of the building blocks I just covered, Zool, our chaos, our ecosystem around Cassandra, EV cache, Eureka, all of that is open source and available through our open source website. This version of the website, it was just finally revamped last week. This version we call the technical indigestion because just so much stuff. We finally split things into category, make things much easier to discover for you. And so I hope you go and take a look and see which of these components, because they can be used individually, make sense for your particular companies and applications. If you like this talk, we do have quite a few other Netflix talks given tomorrow and Friday. You may find some of these useful for you as well. So to summarize, if you do want to improve your resiliency and availability, you need to embrace isolation and redundancy. We hope that you'll find that some of our open source components will help you on that journey. We hope that if you make any changes, that you contribute them back, and this way all of us can benefit from the same ecosystem. And I think I have a couple of minutes for questions. Thank you.